Okay, guys, welcome. Today, we're going to introduce our first chapter where we're going to talk about functions and graphs. And specifically today, we're going to talk about functions specifically. So by the end of this section, you should be able to do a couple things. So you should be able to evaluate a function when it's defined by some sort of formula. You should be able to determine when two functions are equal. You should be able to, we'll go into this a little bit more as we move on, but we want to be able to determine the basics of what we mean by a domain and range of a function, and also to be able to do some things with functions when they're defined by table. Okay, so the first thing that I want to discuss is what we mean by a function. So a function is something that associates every number in some set of real numbers called the domain of a function with exactly one number, right? So what does that mean sort of in English? What we mean in English by a function is some relationship between x and y and it doesn't necessarily have to be x and y, but typically that's what we denote as our input and our output variables. So I'll say between an input variable which again is usually x, and an output variable which is usually y. Oops. Usually y. And the idea behind a function is that for every input variable, there's exactly one output variable, right? Now that's not to say, so let's just make a note of that. So each input variable is assigned to exactly one output number or output variable. And the idea here is that you can't have an input variable go to more than one output variable, right? So for example, you can't plug in an x value of 1 and it spits out two output variables of 2 and 3 or something like that. So that would be a case where you don't have a function. Now, briefly, what we mean by the domain of a function. So the domain of a function is basically the set or the collection. So it's the set of all permissible input values. We'll say input variable values. Right, and we'll talk a little bit more about what this means specifically a little bit later, but it's essentially the set of x values or the set of input values that you're allowed to plug in without anything sort of bad happening, right? And they don't mention it just yet, but we might as well mention it while we're here. Sort of the other side of this, which is the range of a function, is the other side of this. This is the set of all possible output values. Right. And again, we'll sort of say a little bit more about this as we move forward, but that's sort of the basic idea. Okay, so let's look at an example. So in this first example, we're told that we have this function f, which is defined by the formula f is equal to x squared, for every real number x. So this every real number x means that we have any possible number that you can think of, we could plug into this, right, as long as it's a real number. So the first thing that we want to do is something that's essentially very basic here. We want to just evaluate our function based on this formula, right? And the first example, we want to find f of 3, right? Now, all this means is we're going to go to f of x, and instead we replace any x's with 3's. So f of 3 is equal to this function f of x, but except replace x. So instead of x squared, we're going to have 3 squared, right? So 3 squared, of course, just 3 times 3, which is 9. All right, so that's not too bad. For part B, same idea. We have f of negative 1/2. So the idea is very much the same here. So we're going to have negative 1/2 squared this time, which is 1/2 times 1/2, or I should say negative 1/2 times negative 1/2. So the negatives will cancel out and make a positive. And then to multiply fractions, you just multiply the two tops together and multiply the two bottoms together, and that's your new number. So this will be, of course, 1/4. All right, now part C is a little bit different because now we have sort of a variable expression that we're plugging in. All right, now the idea is still the same. You're still going to replace x this time with the 1 plus t, so whatever's inside the parentheses will just get replaced, right? Now, if you want, you could leave it like this, or you could FOIL this out, right? So 1 plus t squared is the same as 1 plus t times 1 plus t. And we could FOIL that out. We could do 1 times 1, which is 1. 1 times t, which is t. T times 1, which is also t. And then t times t is t squared. And then we could combine like terms, and we could say that t squared plus 2t plus 1 is what we get when we evaluate this function. All right, and last but not least, we can do the same thing. This time, we want to evaluate this at x minus 5 over pi. All right, again, don't let the weird inside confuse you. We still want to do the same thing. We're just taking whatever's inside, and we want to square this. All right, so again, what does this mean? This means that we're multiplying it by itself. And again, we just discussed how do we multiply fractions. Well, you multiply the two things in the top together, and then the two things in the bottom together. Right, now on the top, you're going to FOIL again, and you can check that you're going to get x squared minus a 10x plus 25 once you combine all of your like terms. And then in the bottom, you're just going to get pi times pi is pi squared, which is just some gross number in the calculator that we'll leave as pi squared for now. All right, so that's the first example on evaluating some of these function values. Okay, now in the second example, we have something that looks pretty gross, right? So we have, this is what's called a piecewise function. Right, and the reason why it's a piecewise function is because if you look on this sort of side right here, you see that depending on what your x value is, your function values or your output values are slightly different, right? So this is giving us a basically the tax bracket system in 2016, right? Where X is considered sort of an income level. So if your income falls between certain X values, that would be sort of the tax rate that you're taxed at, right? So for example, in part A, they want to know the federal income tax for a single person whose taxable income that year was $25,000, which is just a fancy way of saying we want to evaluate this function g when our x is 25,000. So now we look at our table. Well, where does x equal 25,000 fit in? And it, of course, fits in this range right here. So that means that we need to use that part of the function for this x value. So we're going to have 0.15 times x, which is 25,000, minus 463.75. All right. Now, of course, this is something that we could use the calculator for, which I'm going to do here. We can take 0.15 times 25,000, and that will give us a 3750. And then we want to subtract 463.75. So if we do that, 463.75, we get $3,286.25. And that would be the income tax for somebody that made $25,000, right? Now in part B, we want to do the same thing except now for 50,000. Well, of course, that's going to be different now because now we need to look for when is our x value 50,000, when does that fit in? And that's, of course, going to fit in here. So now we need to use a different function than the last one. So we need to use 0.25 times x, which is now 50,000. And then we need to subtract $4,228.75. All right, so if we punch this into the calculator, okay, so this will give us a 12,500. And then we want to subtract 4228.75. And that will give us a taxable income, or I guess the federal income tax of $8271.25. All right, so this is an example of, again, what's called a piecewise defined function, or just a piecewise function. And that essentially means that depending on what your x value is, your function will be defined differently. All right, so that's another example that comes up. Okay, so in example 3, we want to give an example of a function h whose domain is the set of real numbers, and such that if we plug in 1, we get 10. All right, so when we plug in 1, we get 10. When we plug in 3, we get 2. And when we plug in 9, we get 26. All right, now there's an infinite number of answers you could do for this. Number of possible answers. Okay, now one thing that jumps out to me is that there's no obvious relationship between these x values and y values, right? So this is telling us that we have 3 points. We have 1, 10, we have 3, 2, and we have 9, 26. All right, so those are 3 sort of relationships that we have here. Now, like I said, there's no obvious relationship. So what we're going to do is we're going to basically just define, whoops, I don't know what's going on there. We're going to define a piecewise function that will make this work. All right, so I'm going to define my h to basically just be what I want. I need it to be 10 when x is 1. I need it to be 3, or sorry, I need it to be 2 when x is 3. I need it to be 26 when x is equal to 9. And now I have some freedom, right? Because again, we want the domain to be the set of all real numbers, right? So I've only have 3 x values here, so I need to account for the other x values. So we can just make this, again, doesn't really matter. I can make it 0 for x not equal to 1, 3, 9. All right, and that is something that works. And again, if you find what the relationship is between those 3 points, you could probably construct something that's much more thorough than this. But again, this is something where you have an infinite number of possible answers. Okay, so a little bit more on functions. A lot of people find it helpful to visualize a function as a machine, which basically takes an input x, you put in one input and you get exactly one output, right? So that's sort of what we talked about before. And you can't have something, so you can't have an x going in to your function machine and 2 different y values coming out. I don't know why it keeps doing that. All right, so this would not be able to happen. All right, so that's sort of a nice visual with your function machine there. Okay, now the next thing that we need to discuss is when exactly are 2 functions equal. So 2 functions are equal if they have the same domain and they have the same value at every number in that domain. All right, so we're going to find that functions that may look very similar are not equal because their domains are defined differently, and possibly functions that look very different are equal because on their restricted domain, they're equal on each one of those values. All right, so let's look at an example. So in example 4, we're told that the function whose domain is this set of real numbers has f being defined as f of x equaling x squared. All right, now g is the function whose domain is the set of only positive numbers. So that should be a red flag right there. And then, of course, g of x is still defined as g of x is equal to x squared. All right. So now the answer to are they equal, of course, is no, because they have different domains. All right. So that has an easy answer there. Okay. Now in example 5, we're told that we have f and g are, of course, f of x is x squared and g of x is 3x minus 2. And the domain is just the 2 numbers 1 and 2. Okay, so if we look at f of 1, of course, is 1 squared, which is 1, and f of 2 is 2 squared, which is 4. Now, if we look at g is defined differently, but if I plug in 1, I'm going to get a 3 times 1 minus 2, which is 1. And if I plug in a 2, I get 3 times 2 minus 2, which is 6 minus 2, which is also 4. So in this case, g of 1 and f of 1 are equal. And f of 2 and g of 2 are equal. So these are equal functions. Right? So even though they look very different, because they have the same domain and they are equal on those domain values, then they are equal functions. Okay. Now for example 6, we have that f of x is 3 plus x squared and g of t is 3 plus t squared. All right. Both of their domains is the set of real numbers. So that part is good. And of course, these are going to be equal functions. right? And of course, the idea is that x and t are sort of arbitrarily chosen, right? Because so x, let's put it this way. So x and t are arbitrarily chosen. So it doesn't necessarily matter that one is x and one is t. Right, so that's fine. Okay, now one thing that we need to talk about a little bit is that the domain of a function is not always specified, right? So we need to be a little bit careful there. So if we're not given a domain, what we need to do is, so it's assumed that domain is all real numbers that make sense. And I'll put that in quotes, that makes sense. Now, what do I mean by numbers that make sense? I generally mean where you don't have any bad x values, right? So in general, when you're looking for the domain of a function, what you need to do is essentially find those bad x values and then remove them from the set of all real numbers, right? So what are some examples of bad x values? Well, the most common is an x value that would cause division by 0, all right? So you would want to rule any of those x values out. The next thing is that you would also want to rule out any x values that would cause a negative number inside of an even root, right? So for example, like if you have square root of -4, obviously that's no good because you can't take the square root of a negative number, right? And we'll sort of talk a little bit more about the reasoning for something that specific later, but in general, you would want to rule that stuff out for a domain. All right. Now, this last thing is something that we'll look at later, and that's when you have a non-positive logarithm. So we haven't talked about logarithms yet, but we'll pick up on that later. Okay, so a couple examples of this. For example, we want to find the domain of the function f of x is equal to 3x minus 1 all squared, right? Now this has an easy solution. There's no possible division by 0 because there's no fraction here. All right, there's no fraction. There's no possible even roots of negative numbers. Right, because there's no roots at all. And there's no logarithm. Right, so that means that there's no bad x values. So then your domain is all real numbers. Right, a lot of times they will use sort of this double symbol, or sorry, this double barred R to indicate all real numbers. And a lot of times you'll see what's called interval notation, which is something that you should be familiar with. And that's indicated as -infinity to infinity, right? Because there's no numbers to rule out. All right, now in the next example, we have this h of t here. Now clearly you can see that you have a fraction. So division by 0 is possible. Right? When would division by 0 happen? It would happen when t minus 4 is equal to 0. right? And of course, when is this true? This is true when t is equal to 4. So that means we want to exclude this. So the domain is all real numbers as long as t, as long as okay, so lost a couple sentences there. That's all right. So as long as all real numbers, as long as t is not equal to 4. Right? And then, of course, how could you say this in a more sophisticated way? You could say this is the real numbers minus the value t equals 4. Or probably the more preferred way is in interval notation, where we would say negative infinity to right up to 4. And again, don't include that, and then union that with a 4 to positive infinity. Right? If you have trouble with interval notation, I always say try and imagine it on a number line. Right? Because on a number line, all x values are fine except for 4. Right? So that's sort of how you can visualize that interval notation. Okay. Now, the next example, we want to find the domain of g of x is equal to square root of x minus 5. So, of course, the obvious issue here is that you want, or let's say you don't want x minus 5 to be negative. Right? So in sort of mathematical terms, we want x minus 5 to not be less than 0. Right? Of course, the other way of saying that is if you don't want it to be less than 0, you want it to be greater than or equal to 0. Right? So when is this true? We'll add the 5 over. And this is true when x is greater than or equal to 5. Right? So that would be one way you could say the domain. And again, what's the more sophisticated way of saying this? Well, if we have 5, and it's whenever it's greater than or equal to 5, we would have a closed circle on 5, and then any number above it. So in interval notation, we would bracket this 5 and take it out to infinity. So it would be another way we could say that. Okay, so those are a couple examples of finding some domains. Okay, now for the range, again, that's where we said earlier that we had all the possible y numbers that you can basically get from plugging in a certain x value, right? So one way that we can find the range, so one method is to set your function equal to a certain y value. You want to see if it's in the range or not, to a certain y value that you want to see if it is in the range. And solve for x. So that's what we're going to do in this example here. So we're supposing that the domain of f is the interval from 2 to 5, with f defined on the interval by 3x plus 1. All right. So in part A, we want to know, is 10 in the range of f? Right? Well, again, f of x is equal to 3x plus 1. So if we set 10 equal to 3x plus 1, what do we get for an x value? Well, we would subtract 1 And then we would get 9 is equal to 3x. And then if we divide both sides by 3, we get x is equal to 3. All right, so now the question becomes, is 3 in the domain? And of course, our domain is 2 to 5, and 3, of course, is between those numbers. So the answer, of course, is yes. So then that means that 10 is in the range, because we are able to find an x value in our domain that brought us to that value of 10. All right, now in part B, we want to know the same, but for 19. Well, if we set 19 equal to f this time, right, which is 19 equal to 3x plus 1, we could subtract 1 and divide by 3, and you should check this on your own. You should get that x is equal to 6. All right, but now 6 is not in the domain. So 19 is not in the range. Okay, now finally in part C, we want to know just flat out, what is the range? All right, now later on we'll talk about some sort of better methods for finding this, but in this particular example, let me put a little bit more space here. In this particular example, it's not that hard to sort of visualize what's going on with this 3x plus 1, right? So if you were to graph 3x plus 1, right, and we'll talk more about how to do this later. Right, you're going to get something that looks like this. All right, so a key feature of this is that it's always increasing. So since it's always increasing, to find the range, we need to find the lowest value and the biggest y value. And then range is everything in between. All right, so we're going to get our lowest value when our x is the smallest possible value, and that's 2 in this case, right? So we get a 3 times 2 plus 1, which is 7. So that's our lowest y value. We're going to get our largest y value when x is largest possible, which in this case is 5. So we get a 3 times 5 plus 1, so 16. So then our range is 7 to 16. So that's in interval notation, right? If you wanted to see us on a number line, it's all the numbers between 7 and 16. Right, so something like that. All right, so that's a basic example of finding the range. Okay, another quick example of this is we're given that g of x is absolute value of x minus 5, and the domain is 1 to 20. All right, and we want to know is 2 in the range. Well, we set 2 equal to absolute value of x minus 5, right? And to solve an absolute value equation, you can either have x minus 5 equal to positive 2 or x minus 5 equal to -2. All right, and it turns out that either one of these, if you solve them, this one, if you add 5, you get x equals 7. This one, if you add 5, you'll get a positive 3. And these are both in the domain. And you only need one, so 2 is in the range. Okay, one last example. I think this is one last example, or two more examples. Okay, so in example 12, we're looking at a function now, this time defined by a table, right? Now again, key defining feature for a table is that your x values in the left column, that's your domain, and your y values are your range. Okay, so what this means is that you have a function, they just say to describe it in this example. So the idea is that if you have f of 2, you get 3. If you have f of 7, you get just the square root of 2. And f of 13 is a -4, right? And that's just something that you can just read off right from that table. Okay, so, and this is just what I sort of explained here. This is that if you're looking at a table, the domain of the function is everything in the left column, or the x column, and your range is everything in the right column, which of course is your f of x column, or your y column. Okay, so now in this case, what's the domain? Well, the domain is the left side of your column, so that's x equal 1, x equal 2, x equal 3, and x equal 5. All right, and then in part B, we want to know what the range is. And of course, those are just the numbers y equals 6. And of course, 6 repeats again, so I don't need to write it again. And y equals -7. And then another 6, so I don't need to repeat that. All right. Now, one more comment here. Notice that f is still a function, right? And you might be asking yourself, well, how is this still a function when we have these 6 repeating? All right. The fact that y repeats doesn't matter here. This is still a function, right? Because again, the idea is that I only plugged in one x value for each 6, right? I didn't have an x value that gave me 2 possible numbers. Now, if x repeats, that's a problem. That means that it's not a function. All right, so that's one thing to note there. All right, but that includes this video on an introduction to functions. I hope you enjoyed, and I will see you next time.